Alright, so today I will be going over ATP synthesis and how every molecule of ATP is made throughout glycolysis, acetyl-CoA formation, and the citric acid cycle. So first up, in glycolysis, first we will go over the ATP using steps. The first step that uses ATP is glucose to glucose 6-phosphate. And as you can see here, a phosphate group is added to glucose 6P from ATP. And this is catalyzed by hexokinase. The second ATP using step is fructose 6-phosphate to fructose 1,6-biphosphate. And you can see here that a phosphate group is added to fructose 6-phosphate to make fructose 1,6-biphosphate, and that phosphate comes from the ATP. Next up, we have the NADH producing steps. There is only one of these in glycolysis, and that is glyceraldehyde 3-phosphate to 1,3-biphosphoglycerate. And that is catalyzed by glyceraldehyde 3-phosphate dehydrogenase. And next we have the ATP producing steps, and there are two of those. That would be 1,3-biphosphoglycerate to 3-phosphoglycerate. This is catalyzed by phosphoglycerate kinase. As you can see here, we have dephosphorylation of 1,3-biphosphoglycerate and dephosphorylation of phosphoenol pyruvate. Going over the totals of glycolysis, we have 2 molecules of NADH, 2 molecules of ATP, and these 2 molecules of NADH will lead to a total of 5 ATP molecules being produced. So we have a total of 7 ATP molecules. Now, before moving on, I do want to mention that 2 molecules of glyceraldehyde 3-phosphate are formed from 1 molecule of glucose, and this is why you will see the values of NADH and ATP doubled. Moving on to acetyl-CoA formation, we have one reaction, and that gives us an NADH molecule. You can see that it is pyruvate going to acetyl-CoA, and that is catalyzed by pyruvate dehydrogenase complex. Moving on to the acetyl-CoA formation total, we have 2 molecules of NADH produced, and that leads to 5 total molecules of ATP being produced. All right, moving on to the citric acid cycle. Our first reaction is isocitrate to alpha-ketoglutarate, and this is catalyzed by isocitrate dehydrogenase, and this reaction gives us 1 molecule of NADH. The next reaction is going to be alpha-ketoglutarate to succinyl-CoA. This is catalyzed by alpha-ketoglutarate dehydrogenase and gives us 1 molecule of NADH. The next reaction is going to be succinyl-CoA to succinate, and this is catalyzed by succinyl-CoA synthetase, giving us 1 molecule of ATP. The next reaction is succinate fumarate, catalyzed by succinate dehydrogenase, giving us 1 molecule of FADH2. The next and final reaction is malate to oxaloacetates. This is catalyzed by malate dehydrogenase, giving us 1 additional molecule of NADH+. And going back to what I mentioned about glyceraldehyde 3-phosphate, there are 2 molecules of glyceraldehyde 3-phosphate formed, so that is why these values are doubled in the totals. So when we look at the total, we can see that 2 molecules of FADH were formed, and these 2 molecules will go on to form a total of 3 ATP molecules. 6 NADH molecules were formed, which will go on to create a total of 15 molecules of ATP. And we have a net gain of 2 ATP molecules that don't come from FADH and NADH, and this gives you a total of 20 ATP molecules for the Krebs cycle. If we look at the ATP totals throughout each process, we have 7 ATP molecules coming from glycolysis, 5 ATP molecules coming from acetyl-CoA formation, and 20 ATP molecules coming from the Krebs cycle / the citric acid cycle. And adding this together, this gives us a total of 32 ATP molecules per 1 molecule of glucose.